Hello, here we're going to take a look at 3 AP Calculus multiple choice questions that all have to do about analyzing graphs. They all take a little bit different type of thinking for them, but they are all the same type of great fun. So here we go. First of all, the graph above gives the velocity v in feet per second of a car. Of the following, which is the best estimate of the distance traveled by the car from t equals 0 until the car comes to a complete stop? This is understanding that if I'm given velocity, how does that relate to the position function? Well, the integral of velocity is the position function, because you know that the derivative of the position function is velocity. So since we have this, then we need to recognize that the area under the curve, the area under the velocity function, is the total distance. So the integral from a to b of v of t is equal to the total distance covered. With that, you're like, okay, easy. So I'm just going to take the integral from 0 to 8 of v of t dt, and that will be my answer. The total distance covered. Problem is, I do not know what my velocity function is. Okay, so that means, what does it mean to take the integral from 0 to 8? That is just the area under the curve. So I'm going to look at the area under my curve, and I'm going to start counting blocks. That's what you got to do in this problem. So I have 1, 2, 3, 4, 5. Because see, what we're going to do, we're estimating the area under the curve. And it's easiest to count these chunks instead of like a left-hand approximation or something. So I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. I'll count pretty much full blocks first. 14, 15, 16, 17, 18. Now we can go back. We'll take that as 19. This is 20. And 21 to fill in that small chunk, that little chunk, and maybe this. So we see approximately 21 is the area under the curve, but then recognize each of these blocks has a width of 1 but a height of 10. So each actually has an area of 10, so 21 times 10 gives me 210 feet. Okay, and we did take some liberties estimating there, but 210 is pretty much all by itself there. It's 30 above that one and 50 below the other, so I can pretty confidently say 210 is a good approximation. 2 more graphs here. The first one deals with the first derivative and the second with the second derivative. Alright, so 85. The graph of f prime, the derivative of f, is shown above. The function has a local max at. We know that on the graph of f prime, x-intercepts are either maxes or minimums. Okay, so all we have to do is look at all our intercepts, one right there and one right there, and then determine, is it a max or min? Well, in this case, since the function is here decreasing and here increasing, okay, because this is the graph of the derivative, so where it is negative, that means it has a negative slope. So at this point is going a negative slope and then becoming a positive. That's what the f of x would look like. And then at the other intercept, here it's positive, so positive slope going to a negative slope. This is what f of x would look like, which means this is a max, and the first one we drew is our minimum, which means at x equals 1, we have the maximum which we are looking for. So C is our answer. Now, 87 says I have the graph of f double prime, the second derivative of f. What are all the intervals on which the graph of f, so the original function, is concave down? Okay, how do I figure out where it's concave down? Remember, if f double prime of x is less than 0, the graph is concave down because the rate of the slope is decreasing. If f double prime of x is greater than 0, then it's concave up. What does that mean on this graph? Well, all that means is if it is negative, then it's concave down. Okay, so it's negative here and here. So that means it's concave down on those intervals. So I'm going from -2 to -1, and then I'm going from 1 to 3. So that looks like E, -2 to -1, and then 1 to 3. All right, the final graph we're going to look at. The figure above looks at the graph of f prime, the derivative of function f, before I even of the following, which best describes the graph of f on the same interval. So I take a quick look through these options, and I see that they all have to do with relative minimum, relative maximum, and points of inflection. So before I even try and parse out these options more closely, I'm just going to look at my graph and identify all the max and mins. So we already did the max and mins on that first graph, and we know they are the intercepts. So in this case, I'm going from increasing to decreasing. So it's easy to draw that out, increasing, decreasing. That is a max. Right here, I have another clear intercept. And right here, I'm going from decreasing to increasing. So that's a minimum. What about this x-intercept? Well, in this case, my derivative is decreasing to decreasing. It is not changing, so it is not a max or min. Now I've got to look at points of inflection. Points of inflection on the first derivative are the max or mins of the first derivative. Okay, so right here is a minimum on the first derivative, which means the slope of the first derivative is switching from decreasing to increasing. See that? The slope is switching from decreasing to increasing. So on the original function, the slope was slowing down and then it started picking up again. So this is a point of inflection. Right here, the slope is going from increasing to decreasing. So again, a point of inflection. And then down here at my other minimum, another point of inflection. So points of inflection on the first derivative are wherever there are maxes or mins. That means you have a point of inflection on the original function. So after all that, I see I have 1 max, 1 min, and 3 points of inflection, which line up with option A.